trying to find that angle. Now, if I did Pythagorean theorem, if I did 12.8 squared plus 11.314 squared, took the square root, I should get 17.04. However, that angle right there, I will cleverly call it phi 1. I know that the tangent of phi 1 is the opposite 12.8 over the adjacent 11.314. So phi 1 is the arctan of 12.80 over 11.314. Should be somewhere around 0.8.
Yes, 0.847.
Let's go one more.
Oh, well, then in that case, 0.8469.
Okay. Units?
Degrees? Degrees?
No.
Wait,
Not- Radians I would accept, or you could just say units. Definitely not. The 0.8 angle would
Oh, yeah.
put it really close to the x-axis. All right, so 0.8469. Oh, actually, I put it really close to that and right there. So the phase shift here is going to be pi over 6 plus, because this is at pi 0, pi over 6, and then plus an additional 0.8469, 0.8469. And what do we get as the phase shift?
About 1.371.
Let's go one more.
Oh, well, in
Three seven.
that case, 1.3705.
Okay. Oh. Okay, fine. So the current coming out of the power supply, the formula is 17.04 amperes cosine of 376.99 radians per second times time plus 1.3070.
1.3705.
Just gonna carry away with the zeros. 705. That is the formula. We can now find the current from the power supply at 0.02 seconds by plugging 0.02 in for time. And we get negative 14.87. Please.
Negative 14.83.
Negative, I just said 14.83.
Yes, sir.
Notice if we add these two together, we're not exactly there, we're off at the hundredths of an ampere place, but that's a rounding thing. Questions here? Now, as usual, I think I'm picking up what you're putting down. I feel the vibes coming and you're going, hey, this is great, but where's the inductor? I think we need to bring an inductor into it. about to erase most of this. Anyone still need it? All right, let's go for the
RLC series AC circuit.
power supply.
I have resistor, I have inductor, capacitor.
Now, I did it as I'm going clockwise in RLC order, it doesn't have to be the order in which these show up, it's irrelevant. It's still called an RLC series circuit even if the order's not the same. Yeah, I guess if you said an LRC, people might look at you strangely and they go, oh, yeah, it's the same thing. Right, so if, let's pretend that this is a question for, on a quiz or a test. It took, the first thing is draw the phasor diagram. We can break that down more specifically of what, between current and voltage, what's gonna be the same for everything. Series circuit. Why? Why? Because of the way I'm reacting?
Yeah, I feel like if I remember correctly, I think I know.
In my head, when I'm going over this, I look at it and I'm thinking, all right, I first check series circuit. If I have a current flowing across one, is it gonna flow across the others?
Yes.
Okay, there's no junction
Yeah.
in between, so current's the
It
same. I'll draw up my phasor axes. I know, the 252 textbook always draws that first phasor on to the right. I just don't care for that for whatever reason. It actually makes sense, if we were solving these using complex numbers, then yeah, it doesn't make sense, but I'm still gonna put it around 30 degrees. Oh, by the way, how many phasors will I have?
Eight.
Yes. Two for each. So that's my current phasor for the power supply, which is the same for the resistor, which is the same for the capacitor, which is the same for the inductors. There's 4 of them right there. I just label them as I's if they're all the same. Now let's lay down some voltage phasors. Which one is in phase? Of my 4 voltage phasors, which one will be smack down on top of that? Which one is not represented by Eli the Iceman? Yeah, resistor. For the resistor, voltage and current phasors are in phase. That's what that says for those who couldn't read it.
Oh.
I guess you had to be there when I wrote it down.
Yeah.
So voltage for the resistor, okay. Now, we have Eli, we have ice. Let's do the inductor next. For the inductor, in which direction will the voltage phasor for the inductor point? Or it will be a second or fourth quadrant?
What was the question?
Where am I gonna put the voltage phasor for the inductor? Eli's go.
The voltage leads, right? Because it's Eli. That's
Yes.
so the voltage would be.
Okay. That is it. So it's supposed to be a right angle there. So there is the voltage phasor for the inductor. And again, the E in Eli comes from E for EMF, which is a voltage. Where is the voltage phasor for the capacitor?
Current leads. So
Yes, current leads. Current comes before the E, I before E, in dealing with C.
That means that it will be 90 degrees from, current will be 90 degrees from voltage.
Right. And it'll be 90 degrees, and so current leads, again, these
Oh, so he's can't-
arrows that are spinning around counterclockwise, and so I can draw it in the right direction. All right, so V sub C, that is a right angle there. So now we need to be able to figure out where is the EMF for the power supply. I know that if I go to Kirchhoff's rules, that whatever voltage, if I take these 2 points here, my voltage across here must be equal to the voltage across all 3 of those. In other words, the voltage across here is the sum of those voltages. So I have to add these 3 phasors. Well, adding VL and VC, relatively simple. They're in opposite directions. Think about like adding vectors. So whatever the magnitude of VL and VC are, I know that the sum of them is just going to be the difference of the magnitudes. Now, I don't know which is bigger. I don't know if VL is bigger or VC is bigger. When doing the phasor diagram, pick one. I'm just going to assume VL is bigger. That could be wrong, but I'm just going to assume that for right now. Let's see. Like blue. If I throw in all the blues over there. Got it. Well, this red one does. So I'm just going to add these 2 together, and I'm going to say that that is going to be VL minus VC. So again, adding like vectors that are opposite directions, so I'm subtracting magnitudes. My power supply, so that's the sum of those 2. Now I add VR. And that would be the voltage for the power supply. Basically added thinking of them as vectors, I just added the 3 vectors together. Oh, really know they're phasors. So let's make sure I've got 1, 2, 3, 4 voltages and 1, 2, 3, 4 currents. I got 8 phasors. All right, next step. And again, I want to emphasize, if VC is bigger, then that phasor is going to be pointing down here. I didn't give you anywhere near enough information. All right, so let's go to finding the impedance. Well, we got a little Pythagorean theorem going on right here. That's a good place to start. I know that VL minus VC squared plus VR squared is equal to V power supply squared. Now I do the Ohm's law bit. So first, the general rule is you find a Pythagorean theorem bit, then you put in the Ohm's law bit, and so that's I L X L minus I C X C 1V squared plus I R V R squared equals I E S Z that quantity squared. Now, all the I's are the same. Because it's a series circuit, I know the currents are all the same, so I'm just gonna divide everything by I, or factor I out and then divide, however you wish to do that. But I'm gonna be left with XL minus XC squared plus, oh, that's wrong. That should be an R there. Plus R squared equals Z squared. So my impedance equals the square root of, usually R comes first for whatever reason, R squared plus XL minus XC squared. But I have a formula for XL and XC, so let's do that substitution. So my impedance is the square root of R squared plus omega L minus 1 over omega C squared.
Which is just R plus omega L minus 1 over omega C.
Squared. Oh, no. You
Right, I can't do that.
you can't do that.
My brain.
Despite the number of students who have tried to convince me otherwise. Math does not work that way. If you did that on a test, you might get the, not how math works.
Quite familiar.
All right, so let's use some numbers here. Let's figure out what the total impedance is. I know that R is, let's make R 15 ohms. Well, the capacitance, 200 microfarads, just as before. And the inductance, again, I've already done some numbers on this, 45 millihenries. 45 millihenries.
They're called what?
Henries.
Henrys. I thought you were saying hippies.
No. And remember,
He might have been, I don't know.
the inverse of it is airnet.
Yes.
Oh, that's right. That's right.
So that would also therefore be 0.045. Here, that is negative. There you go. So if later on you start teaching physics, you could say at
Right.
least you've seen it once. It's
Yeah.
actually in use. In order to figure out omega, we need to know what the cycles are. So let's just make let's make it international. It's a European problem.
Oh.
So the frequency is 50 hertz. And that's out there. There we go. And Europe is three different shades of blue here. Looks like 240 volts. All right, so the frequency is 50 hertz. Then, what is the angular frequency?
It's 2 pi times the frequency, right?
Yes.
Should be like 314 point something, because that's just 50 times 2.
Oh yeah, it would
So
be
it's like
314.159. So 314.159 radians per second. What's the amplitude of the voltage?
That's right.